Hello everyone, this is Jian Shao.
This is Qirui Xu.
We are electrical engineering master students from Columbia University.
This is an introduction of our pulse oximeter-based heartbeat rate monitor system design project of course 6350.
This course is instructed by Professor Peter Kingat, and the chips are fabricated by Moses.
Our chip can monitor the heartbeat rate through a finger clip sensor.
Here is a demo of this system, and you can get a general idea of how the system works. This is our demo for the PCB. When you plug your finger into the sensor, you can see the LED blinks every time when there's a heartbeat, and the LCD display is showing the current heart rate. There are 3 modes of display. This is mode 1. The LCD refreshes every time when there's a heartbeat. Now it is in mode 2. The LCD refreshes when the heartbeat rate fluctuates more than 2 BPM. Now is mode 3. In mode 3, the LCD refreshes every 5 seconds. The 4th button is for reset. This project is based on the principle of PPG technique. This technique is a non-invasive method to detect the change in blood volume in tissues using a light source and a detector. Since the blood volume is changed synchronized to the heartbeat, this technique can then be used in our heartbeat rate monitor. The PPG signal is generated by an infrared LED and a photodetector, and to monitor the heart rate, a finger must be put between the LED and the photodetector. There are mainly 2 types of methods to detect the PPG signal: the transmission type and the reflective type. In this project, we use a transmission type sensor. In transmission type sensor, the LED is placed on one side of the finger, while the photodetector is placed on the other side to measure the light intensity. The change in blood volume with heartbeat causes a small change in the current through the photodetector, which is then transformed into a periodic voltage signal. This time-variant voltage signal is the PPG signal. PPG signal has mainly 2 AC components and a DC component. The first AC component with a lower frequency is caused by the respiration, while the second AC component with a higher frequency is caused by the pulsatile changes in blood volume, which is synchronous with the heartbeat and is the useful signal for our system. These 2 AC components are superimposed on a large DC component which is related to the tissues and average blood volume as well as the biasing circuit. Hence, the DC component and the first AC component must be removed to get a useful AC component with a reasonable signal-to-noise ratio.
The system implementation of our heartbeat rate monitor system. One of the main noise of the PPG signal is caused by respiration and body motion, which has an average frequency below 0.5 Hz. Therefore, we first use a second-order high-pass filter to compress the AC signal from the respiration and get pure AC signal without DC component. After that, we use the first OTA stage with a low-pass filter to increase the amplitude of the heartbeat signal and compress the high-frequency noise in the system as well as the disturbance from the environment. Then, we use a potentiometer to attenuate the amplitude of the signal so that it won't saturate the following OTA stage. After the potentiometer, we use the second OTA stage to increase the amplitude of heartbeat signal to a sufficient large amount. At the same time, we use a high-pass filter and a low-pass filter to remove the noise. After that, we use a comparator with intrinsic hysteresis to change this analog AC signal to a digital signal. The output signal is fed into a microcontroller Arduino Uno, which counts and calculates the heart rate and display it on LCD display.
This is our PCB for the PPG system. Here is our chip. Here is the PPG sensor. These are the periphery circuit for offering the DC power supply and low-pass and high-pass filter in the signal flow. Here is the Arduino, and here is the LCD display. Now we are testing the functionality of our system. This is the signal from the PPG sensor. As we can see, this signal has a large DC content of about 4.5 volts, which is much higher than the power supply level of 180 nanometer technology. And also we can see the signal is going up and down by a certain amount. This is because of the AC component caused by the respiration. The wanted signal is this kind of pulsatile waveform. It has an amplitude of about 10 millivolts. This is the signal after the high-pass filter and the first OTA stage. As we can see, the DC value of this signal is at about 0.9 volts now, and it is no longer going up and down. Now it has an amplitude of 1.5 volts. This is the signal out of the second OTA stage. It has an amplitude of 1.1 volts, and the peak value is larger than the 1.2 volts reference voltage plus the 100 millivolts hysteresis we set. This is the output signal of the comparator. The pulse is synchronous to the heartbeat. Thanks for watching. Thanks Columbia University and Professor Peter Kingat to provide us this opportunity. And thanks Moses for fabricating the chip.
If you have any questions, please check our website and feel free to contact us.